Okay, in this video we're going to talk about how indifference curves can model complements, substitutes, and imperfect substitutes. We're going to go through and actually derive the marginal rate of transformation in a two-goods model. And then finally we're going to talk about the expenditure function, which is a way of thinking about the utility maximization problem from a different perspective. So let's just get started. So the first thing we're going to do is just talk through three different scenarios uh, with three different indifference curves. This is very similar to what's in the textbook, so feel free to refer to that as well. So we're just going to set up three graphs here. We're going to start with 2, and then we'll talk about the third one. So we have a and b, and then y and x. Okay. So first we're just going to set up how we would think about perfect substitutes. So let's call this perfect So let's say A and B are perfect substitutes. What might the indifference curve for A and B look like? Well, if I'm at a point x1 and I move, and let's say there's 10 of A and 2 of B. If A and B are perfect substitutes, when I give up 1 unit of A and we go to 9, how many more of B will I need? Well, just 1. So we go from 2 to 3 for B, and we go to from 10 to 9 of A. This is x2. So we get this linear relationship between A and B. It doesn't have to be perfectly one-to-one, though. You could imagine perfect substitutes maybe not 1 for 1, but 1 for some number, which would change the shape of the indifference curve. But it would look something like this, some linear function. With perfect complements, this is going to look pretty different. Let's call this point A1. And let's say this point is at 4 and 4. If x and y are perfect complements, that means I need more of both to be better off. So if I increase from A1 to A2, where I go from 4y to 6y, if x and y are perfect substitutes, or perfect complements, this new point, A2, doesn't give me any higher utility because I need more of both to do any better. So I'd have to increase both x and y to do any better. So these 2 points are on an indifference curve. And in fact, the indifference curve runs vertical because I need more of x to do any better. And if I don't increase y and I just increase x, then I'm on the same indifference curve because I need more of y to do any better. So these are the two extreme cases of perfect substitutes and perfect complements. In our videos so far, we've we've looked at cases that look more like this, which we call imperfect substitutes. They look more like this. Let's say m and n, where if I give up some of m, we go from point x1 to point x2. I'm giving up some m, and I'm gaining some n. So I'm trading off some m for n. And this trade-off relationship changes as we move along the indifference curve. It's not linear, so there's not a one-to-one, or there's not a marginal rate of substitution that's constant. So what this means is when we're way out in extreme values, at extreme like points very close to 0 for m, the trade-off becomes very stark. Trading off some, drawing all these lines, hopefully this is clear. When we trade off just a little bit of m, we can get a lot of n. So this is generally the type of behavior we would see with imperfect substitutes. Okay, so just a little bit of a note on different shapes of indifference curves. The shapes really do affect the relationships between the two different goods that we're modeling. Okay, so next, I just want to, we brushed over the marginal rate of transformation in tutorial 2, but I just wanted to run through a little bit of some of the background. This is going to take maybe a minute or two. So here, we'll call this maybe deriving the MRT. So you'll remember the expenditure function, the budget line, is y equal p1 q1 plus p2 q2. But you'll also remember that each quantity is a function of how much we're choosing of the other quantity. So we can actually write q2 is some function of q1. So this is, we sort of have this function taking q1 and transforming it into q2. And this is just, we've done this many times, right? The solution of one possibly depends on the other. So what we're going to do is substitute, and you could do this for either q1 or q2. You just need to do for one. We have this sort of implicit function defined for q2, and we're just going to plug it in. So then this is q2 as a function of q1. Okay, so then we take the first derivative with respect to q1 of this function, which gives us p1 plus p2 times the derivative of q2 with respect to q1. And this piece here is our marginal rate of transformation. So we're going to set this equal to 0 and solve for the marginal rate of transformation. So I'm going to rewrite this MRT So the MRT is equal to negative P1 over P2. And in the background, you can be thinking about this as the derivative of Q2 with respect to Q1. And in sort of in the background, I'm always thinking of it as Q2 on the vertical axis and Q1 on the horizontal axis, which is why we're taking the derivative with respect to the x variable here. And this marginal rate of transformation is just the slope of this budget equation here. And this is really where it comes from. It's not that complicated of a operation, but the result is pretty simple. Just this piece here. Okay. And lastly, we're going to talk about the expenditure function. Oops. Can't spell. Okay, so up until this point, we've mostly focused on utility maximization, where we had our indifference curve and our budget line. So we had a budget line and our income was fixed. And we tried to find, so we had an indifference curve that was tangent to some fixed budget line. And we looked at a range of indifference curves. And U bar was the thing we were moving up and down. So we had U bar 1, 2, and 3. And we tried to find the U bar that maximized our indifference, maximized our utility, while living on the budget line. So this point was feasible. We were able to pay for it, but it was also the highest utility we could achieve. The expenditure function comes at this problem from the other angle. So instead of having a range of indifference curves, let me draw this better. Instead of having a range of indifference curves that we vary, trying to find the highest indifference curve, instead we vary the budget line. So here we have different expenditures. You could think of this as Y, or you could think of it as E. Essentially what we're doing is changing this Y. So we could call this Y1. Say this is Y2. And maybe some Y3 out here. And the goal is the same. We're trying to find this point where the budget line and the indifference curve are tangent, but instead of moving the utility around, we're moving our expenditure around. So let's just walk through a simple problem. This is similar to what we did in the last video, except we're going to approach it from this perspective instead. And before we do that, let's just write down one definition here. So we're going to say given prices, the expenditure function finds the minimum expenditure to achieve a given utility, some u bar. Okay, so we're going to work through an identical problem to what we did in the last video, except instead of changing u bar, the indifference curve, we're going to change our expenditure. So we're going to write this as min e q1 q2, and the expenditure function is, or this e is our expenditure. We have p1 q1 plus p2 q2, and this is going to be constrained by u bar. So our utility takes q1 q2, and we're subjecting it to u bar. So that's our indifference curve. And you'll remember utility of this utility that we're working with looks like this. We have 8 q1 1/2 plus q2. And we're just going to define u bar as something. We're not going to worry about this for a second. We're just going to leave it as a variable, undefined. Okay, and at the end we'll plug in some prices and income and utility, and we'll do all of that at the end once we've gone through and solved this problem. So instead of using the Lagrangian method, we're going to use the substitution method. So we have this relationship here, and that allows us to solve for q1 or q2 in terms of the other. So let's rewrite this as, well, first I'm going to rearrange this. So we have q2, which is probably the simpler one, minus 8 q1 1/2. And we're going to use that relationship, plug it in here. So we have u bar, subbing in for q2, u bar 8 q1 1/2. And then all we have to do here is just take the first order condition with respect to q1. So the first order condition here is p1 plus, so this doesn't depend on p1, so all we have left is our negative p2 8. Then we have an exponent of 1/2 q1, and then we subtract 1 from the exponent, which gives us negative 1/2, and we just set that equal to 0. So this is nice. We have p1 on one side, we have p2 8 1/2 q1 negative 1/2 on the other. So we can multiply q1 1/2 on both sides and divide both sides by p1. So we have p2 p1 times 4. Okay. And then we're just going to square this. So we have Q1 star is equal to 16 P2 P1 squared. And this is our solution. And this will look pretty familiar from what we did, similar to what we did in the last video. So we now have a relationship between the prices P1 and P2 and our Q1. So what we did last time with the utility maximization problem is actually to take our first solution for Q1 and plug it into the constraint. So that's what we're going to do here, except the constraint isn't the budget. In this case, it's the indifference curve, which is here. So we're just going to take our value for Q1 and plug that in to the indifference curve. So let's just let's maybe do this over here. Okay, so let's separate these. All right, so maybe a little trick here. We have these two values that are simpler than like taking the square root again. So we'll just plug them in. So we have 4 P2 P1 plus Q2 is equal to U bar. Okay, so then we have Q2 star is equal to U bar minus, then we have 8 times 4, which is 32 P2 over P1. Okay, so then this is our second solution value. Okay, so the expenditure function, this, we're going to call this E star, is a function of Q1 and Q2. And this is the solution value, the expenditure that achieves a given utility bar. So given U bar, what do we have to spend if we're being optimal? So what this is just plugging in, so we have P1 times Q1 star plus P2 Q2 star. So then we just go ahead and plug our values in. So we have P1 times P2 P1 squared 16 plus P2 times U bar minus 32 P2 P1. And we can do a little bit of expansion here. So we have 16. These are going to cancel. And that's going to leave us with 16 P2 squared over P1 plus P2 U bar minus 32 P2 squared over P1. And then we can just simplify this because we have 16 and 32. So this is just P2 U bar minus 16 P2 squared over P1. And this is our E star. Okay. So this is the expenditure function, and let's just go ahead and verify that the values we used in the last video give us the same solutions using the expenditure function. So to do this, I'm going to do this in blue. So our price for 1 was equal to 2. Our price for 2 was equal to 1. And we had a utility equal to 20. I don't think I did this. I don't think I solved for the utility in the last video, so I'm just going to give it to you here. And in the background, we had an expenditure of 12. Okay. So let's plug these values in to each of these quantities. So we have Q1 is equal to 16 times 1 over 2 squared, which comes out to be 4, which is good. That's what we're looking for. Means we did our math correctly. And U bar, which is 20 minus 32 times P2, which is 2 over 1. Let's see. Nope, I did that wrong. Thought something looked fishy. Okay, P2 is 1 and P1 is 2. So that comes out to be 16, and again, this comes out to be 4. So that's great. And our quantities are verified. So next, what we want to do is find our total expenditure. So let's plug this in, plug our utility and price values in. So we have P2, which is 1, times U bar, which is 20, minus 16. Then we have P2 squared, which is just 1, over 2, which, I'll have to jump down to the next page, we have 20 minus 8, which is 12. And again, that verifies our expenditure. Okay, so we're done for material this week. We're going to pick up with chapter 4 on the demand curve in our next set of videos.